Hey AP Calc students, time to look at another FRQ. This time we are looking at AP Calc AB, the 2016 exam, question number 1. So, here's what they want. It says, first off, you should know it is a calculator question because it is number 1. And it says water is pumped into a tank at a rate modeled by the function w of t equals 2000 e to the negative t squared over 20 liters per hour for 0 less than or equal to t less than or equal to 8, where t is measured in hours. Water is removed from the tank at a rate modeled by r of t liters per hour, where r is differentiable and decreasing on 0 less than or equal to t less than or equal to 8. Selected values of r of t are shown in the table above. At time t equals 0, or when this time begins, there are 50,000 liters of water in the tank. Now, when you first read this question, it almost sounds like a two-rate style question, and you could argue that it is, but this falls under the category of a table of values. It's actually a blend of a table of values and a two-rates question. And the reason we call it table of values is that instead of giving you one of the rates, they just give you selected values from it. And they're going to have you manipulate the graph. And so it is a blend, and you're going to see how they kind of tie together. So the first thing I like to do whenever I get a table of values question is I like to make a graph just to see what's going on. This one's fairly simple. Looks like our time here is 0 to 8, so our x or our horizontal axis will be pretty simple. And then our vertical axis, we're going to go from a low of 700 to a high of 1340. So I'm just going to make a little graph over here just to help me visualize what's going on. And so this is time, and I've got 1, 2, 3, 4, 5, 6, 7, and 8. So there's the hours. And then this is the graph of the rate. So I'm going to call it R. They're calling it R, and this is the rate that the water is being removed from the tank. So water in, water out, and this is the rate it's leaving. So it looks like when it begins at time equals 0, that's our highest amount, and it's 1340. And I don't get too concerned about unit or the scale. I just want to get these values on here. So at 0, we're at 1340. At 1, we are a little lower. We are at 1190. And then at 3, we jump to 3, we're at 950. And then we jump to 6, and we're at 740. And then at 8, 2 hours later, we're at 700, so that one's fairly close. Okay, so we have those values, and I'm going to make a point at the coordinate value. So at 1, I was up here at 1340. At 3, or at 1, I was at, at 0, I was at 1340. At 1, I was at 1190. And then it's at 3, I'm at 950. And 6 is 740. So that's about right there. And then 8 is at 700. Okay? So as time goes by, and I'm just going to make a dotted line here, as time is going by, it looks like the rate that the water is exiting the tank here is decreasing the entire time. Okay? And again, it doesn't have to be perfect, just gives us an idea. It's decreasing the entire time. All right. So now let's go back to the question. And it says, for part A, let's see what we have to do. So part A says, estimate R prime of 2. Show the work that leads to your answer and indicate units of measure. Well, usually when you see this kind of question, whenever you have a table of value, they love to have you estimate the derivative. And they want to see if you know your stuff. And what they always do, if they're going to estimate the rate of change, now remember, this is R over here. This is the graph of R. So they're having you estimate R prime, or estimate the derivative. Well, when you estimate a derivative, you can't take instantaneous rate of change without having the function. So in order to estimate it, we have to take average rate of change. So they're asking us to estimate it at 2, which is always right in the middle of an interval of the values that are given. So this is 0. I'm going to just underline the values they gave us on the table. So we had a value at 0 and at 1, at 3, at 6, and 8. Now if you'll notice, they're asking us to approximate the derivative right here at 2. Or in other words, they're saying estimate the derivative, which is the slope of the tangent. Well, if you're going to estimate the slope of the tangent, you estimate by using the slope of the secant, which would be the line connecting the 2 points on either side. So 1 is 1 unit away, 3 is 1 unit away. So it's that simple. To estimate r prime, I'm going to do AROC. So this is just an AROC question. All right, so AROC, and they say, well, r prime of 2 is going to equal just the slope of the secant. So at the coordinate 1, right here I'm going to use these values. My difference of my y values, it's 1190 minus the y value at 3 is 950. And this was the x value at 1, and this was 3. So subtracting these two, 1190 minus 950, I get 240. 1 minus 3, we get negative 2. And I get negative 120. Now, you got to make sure you get your label correct. You have to always recall, similar to a position, velocity, acceleration, acceleration always is time squared, because acceleration is the rate of a rate. Well, if r is a rate, this is the rate the water is exiting, and this is asking me to find the derivative of a rate. Well, then my time is going to be squared. So this is negative 120, and this was in liters, so I'll just put an L, and this was liters per hour, and I'm going to put hour squared. Technically, it's liters per hour, and you have to remember always when you take the rate of a rate, or the derivative of a rate, you are going to have time squared. So there's A. Let's move on to B. Now B says, use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Well, I'm actually surprised in the question that they told you what this represented. That actually would have been a good question to ask you, what does it represent? What does area under the curve represent? Well, you guys should know that what do you get when you integrate a rate? Whatever the rate's producing. Well, if area under the curve is the integral of how much water, the rate water's leaving the tank, is how much water left the tank. So they're asking us to approximate it with a left-hand Riemann sum, and they have everything set up kind of nice that it's going to work out. So since I'm coming from the left, I'm going to use 0. I'm not going to wind up using 8. So since I have 0, I'm going to draw vertical lines at my endpoints, or at my selected values. So 0 already is highlighted from the axis. I have a value at 1. I have a value at 3. And so I don't get confused, I'm going to take off this dotted line we used for part A. I also have a vertical line at 6, and I have a vertical line at 8. And it says to come from the left. So I'm going to come over here. There's my first rectangle. Here is my second one. Here is my third one. And here is my fourth one. So those are my 4 rectangles, my Riemann sum, that I'm going to approximate this. So it looks like the integral from 0 to 8 of r of t dt, we can approximate that with these 4 rectangles. So I'm just going to, each set of parentheses here, I'm just going to put the width and height. So this first one is 1 times, the height was 1340, plus the second rectangle was 2, and the height was 1190. The third rectangle, the width is 3, and the height winds up being 950. And then the last rectangle, width of 2, and looks like a height of 740. All right. So if we simplify these a little bit, we get 1340, and this is a calculator question, so you could throw these in your calculator. 1340 plus, what do we get here? 2200 plus 180, so I think we get 2380. And then 3 times 950, I guess that'd be 3000 minus 150, so that'd be 2850. And then 2 times 740, it's going to be 1480. And if you add all of these up again, you'd probably just throw that in your calculator, and you'd wind up with 8050. So this is approximately 8,050 liters. All right, so 8,050 liters is how many how much water was removed from the tank, and it doesn't say whether it was leaking or it was actually being pumped out. Not really important. All right. So the next part of the question says, though, this is an interesting part. It says, is this value we got right here an overestimate or an underestimate of the total amount of water? Give a reason for your answer. Well, this is another reason why the graph is handy. You guys can see that since the function is decreasing and we came from the left, we're going to have an overestimate. If the function was decreasing and we would have come from the right, we would have been under. So decreasing left, you're over. Decreasing right, you're under. And you can flip those if the function was increasing. Increasing left is under. Increasing right is over. So because the function was decreasing and we were coming from the left, our rectangles went over the top of the function. So my answer here is going to be, this is an overestimate. And I'm going to say overestimate. And my explanation is overestimate because R is decreasing and spell Riemann correctly, R-E-I, and Riemann's sum is from the left. Okay, there's B. Let's look at C. C says, use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Well, this is where we're going to go back to the two-rate style of question. And I'm going to build this equation. Now, if you remember, it's common for a total amount in a two-rate question to be composed of three things. So I have this system where we have 1 plus 2 minus 3. There's three things involved. And the first thing that's involved when you do this type of question is it's going to be how much was there when the day began or the time period began, and you're going to add the integral of increase over the time period, so I'll say from 0 to t, and then you're going to subtract the amount that was being decreased from the function, whatever amount it was, and I'm assuming that the times are the same here. So you just want to say what was there when we started, what was there when we increased, what was there when we decreased. So it says use our approximations here to figure this out, and let's see if we can do that. Well, it says they want to know this at the end of the day. So in other words, when time is equal to 8. So let's see what we can figure out here. So the approximate time here at 8, I'm actually going to put approximate because it's not exact. Now if we go back to reading the question, it says at the time t equals 0, there's 50,000 liters of water in the tank. So they always like to sneak that in, usually, the initial condition. Got to make sure you're paying attention to that. So 50,000, and then we have to figure out how much was in the tank, or how much was put in the tank during the day. Well, this is where it kind of is more like a two rates question, and it gives us a function, which is kind of complicated, exponential, 2000 e to the negative t squared over 20. That is our function of how much water, or the rate the water's going in the tank. So what do you get when you integrate a rate? Whatever the rate's producing. So if we integrate the rate from 0 to 8, the rate the tank is being filled up, that's its increase, we're going to get how much went in. So I'm just going to put W of t dt. And then I'm going to subtract how much was removed in those 8 hours. Well, that's what we figured out on part B, which was 8,050. So 50,000 plus how much was in minus how much was taken out, and that'll give us how much was in there. Well, this is a calculator question, and you guys could just put this in your calculator, and here's what winds up happening. On the bottom here, we're going to get, here's what our numbers turn out to be. 50,000 plus, the result of this integral is 7,836. 7,836, and if we go to 3 decimals, it's 0.195. And then if we subtract 8050, throw that in your calculator, and you can see that the rate that the liquid or water was being pumped in is pretty close to what was being pumped out. So not off by too much here. And so if you combine all of this, your final answer to the nearest liter is 49,000, it's a comma there, 49,786 liters. Okay. There's that one. Okay. So again, from the top, combination table of values and two rates. The rate the water was being removed was represented with table of values Riemann sum approximations. The rate the water was going in was actually a given function, and so we had to estimate the derivative of r using average rate of change. We had to approximate how much water was removed from the tank by integration, but we had to use approximations with Riemann sum. And then number 3, how much was in there at the end of the day? We used our amount equation, and we had a combination of an Riemann sum approximation combined with just integrating a rate, and then we had our initial condition. Now the last part, part D, is a little bit weird. It says, is there a time, t, when the rate that the water is being pumped into the tank is the same as the rate the water is being removed from the tank, and explain why or why not? Well, it's kind of an interesting little question. I want to go back up to our graph here, and I want to point out a couple things. This is actually a fairly easy question, but they're trying to sneak in a theorem that you're supposed to learn in your AP Calc AB journey. Actually, it's a pre-calc is usually where you learn this theorem. So the first thing I want to do is just show in this same interval, I want to graph the rate that the water is being put in. I'm going to change colors here just to make this look a little, to see this a little easier on the graph. So this is going to be part D right here. Well, here's what I know from the table. I know at the end of the day, the rate the water is being removed is 700. That was given. And when the day began, t equals 0 is being removed at 1380. So those are the two numbers there. So here's, I'll just go ahead and write what I know, what I know here. So I know that r of 0 is equal to 1380, or 1340 it is, and that I also know that the rate at 8 is equal to 700. Okay. Now what I'm curious is what is going on with the rate the water is being entered. So I'm gonna figure out what W of 0 is, and then I'm curious what is W of 8. So if you put W of 0 into the function, and the W function's over here, maybe I'll just put that up here for reference, sneak that in up here. Okay, so W of t is equal to 2000 e to the negative t squared over 20. Okay, so if I put 0 in there, this is going to become either the 0, which is 1 times 2000. So at the beginning of the day, the rate the water is being pumped in is 2000. The rate the water is being pumped out, 1340. And now how about W of 8? Well, W of 8, if you put that in here, you're going to get 2000 e to the negative 64 over 20. And again, this is a calculator question. And what that number winds up being, if you put in your calculator, would be 81.524. Okay? Now the reason I'm doing that, just to show you what's going on here, is I'm going to graph these 2 points on here just to show you what would happen. So at W of 0 is 2000. So right up here, I'm going to extend this a little bit. I'm just going to put a point up there and say, well, that value 2000 would be up there if I were to graph it. Okay? And then I'm going to say, well, this point here that is 81.24, that would be down here somewhere. I'm just going to put an 81, and I'm going to say, well, at 8, it would be about right there. Okay? So here's what I know would happen. If I was to graph the rate, the function for the rate the water is being pumped in, it's going from 2000 at the beginning of the day down to 81. Now, it could be oscillating back and forth. Who knows? Actually, we can see it's kind of it's like a decay style function. But in order to get from here to here, I think you guys could see that somewhere during the day, in order for this to happen, there had to be a point where they crossed. Or in other words, the two functions were equal. And that's actually what the question is asking. They're saying, is there any time during the day when the rate that the water was being pumped in was the same as the rate the water was being pumped out? Well, I can see here that there had to have been a time where the functions had to cross. Well, explaining that can be a little bit tricky. And the way you want to explain that is you're going to actually use this theorem that AP Calc tends to love, which is the intermediate value theorem. I want to just real briefly explain the intermediate value theorem. Usually in pre-calc, here's what happens. In the intermediate value theorem, you get this kind of question. The intermediate value theorem says, I have a function that looks like this. And that's A, and this is B. And so this coordinate right here, that would be f of A. And this coordinate down here, that would be f of B. And the intermediate value theorem says, given an interval from A to B, if f of A is greater than 0, and f of B is less than 0, one's positive, one negative, then there exists a value C in the interval A to B such that f of C is equal to 0. Or in other words, if your y value is positive and the other y value at the other end of the interval is negative, then there has to be a 0 in between. They have to be crossing. And so what they want you to do is apply this concept to this problem. So I want you guys to look at the graph right here, and what we're going to do is take this graph and just lower it so that this ambiguous point right here that we don't know, we're going to make that be the x-axis. And I'll show you what I mean. It's a little bit confusing, but I'll show you what I mean. So what I'm going to say is, well, I'm going to start with the value for W, and I'm going to say, well, when the day began, W of 0 minus R of 0, okay, so I did 2,000 minus 1,340. When I subtract those two values, I wind up with 660, I believe, and that is a positive number. And so I'm going to say that is equal to 660, which is positive. Okay? Now at the end of the day, W of 8 minus R of 8, okay, W of 8 right here minus R of 8, that's going to be negative 618.476. Okay, and I'm getting these values from up here. If I subtract them, I get this negative number, and that's less than 0. So what I'm showing is the difference of the functions at the beginning of the day is positive. The difference of the functions at the end of the day is negative. So what I get to say is, therefore, by the intermediate value theorem, there exists a time somewhere between 0 and 8 such that W of t had to equal R of t. If at one time it was positive, one time it was negative, there has to be a time where they were equal, or we're saying there was a x-intercept concept there. And that's how it would work. So once again, there's the entire question A to D, and you get to see how it all kind of fits together. Table of values combined with the two rates. There's your graph, average rate of change question, and as you keep doing these, you're going to see how the same type of things come up. And if you ever get a table of values, guarantee they're going to have you approximate it with either trapezoidal or Riemann sum from the left to the right, maybe the midpoint value, and you're going to have to know what that approximates. Oddly, this question told you what the approximation was, which was the rate the water was being removed. And then since it was a calculator, they gave us a function that you needed your calculator in order to integrate to find how much water was going in. And then it was were they over the same intermediate value theorem. So there it is, 2016, number 1. All right, we'll see you next time.